Occupying less than 0.5% of Europe's land area, the Netherlands has achieved an agricultural productivity that makes the whole world take notice. Every year, the Netherlands supplies around 2.5 billion tulip bulbs to the global market. And with just 14.5 hectares of greenhouses, they can produce up to 100 million tomatoes. What makes this extraordinary is that the achievement does not come from vast farmlands, but from smart greenhouses. High-yield seeds, hydroponics, rock-wool substrates, water recycling systems, and agricultural robots. From vibrant tulip fields to tomato greenhouses operating like laboratories, the Netherlands has transformed every square meter of land into a precision production machine. So how did a small, densely populated country constantly under pressure from the sea become a global symbol of high-tech agriculture? Join Terran Works as we explore this fascinating story in today's video. After decades of dealing with limited land and steadily rising production costs, the Dutch realized they could never win the race of who has more land. So instead of expanding endless fields, they chose to tackle a more difficult question. How can the same small area produce more food, more consistently, and with less waste? From that point on, the philosophy of more yield per hectare became the foundation of Dutch agriculture. Here, farming no longer relies heavily on unpredictable weather or intuition-based experience. Instead, every step is measured, adjusted, and optimized. Every drop of water is delivered precisely where it is needed. Every nutrient dose is carefully calculated. Light, temperature, and humidity all become controllable variables. This mindset paved the way for precision agriculture, where farmers are not simply growing crops, but operating an intelligent production system on every square meter of land. If there is one image that makes the whole world think of the Netherlands, it is the vibrant tulip fields stretching endlessly like giant carpets of color. But for the Dutch, that beauty is only the surface of a much larger industry. Every year, the country supplies around 2.5 billion tulip bulbs to the global market, turning those small bulbs hidden beneath the soil into the foundation of the flower supply chain for many nations. What is fascinating is that Dutch farmers do not keep the tulips blooming until the end of the season. As soon as the flowers reach their peak color, specialized machines move across the fields and cut off the flower heads. What may seem like destroying beauty is actually a precise calculation. Once the flower stops consuming nutrients, the plant redirects all its energy into the bulb, allowing it to grow larger, stronger, and more uniform. Afterward, the tulip bulbs are harvested, cleaned, sorted, and prepared for export. Meanwhile, in the cut flower industry, the Netherlands continues to play a central role through massive flower auction hubs such as Royal Flora Holland, where millions of flowers can be traded, sorted, and shipped across the world within an incredibly short time. From a delicate flower, the Netherlands has built an entire agricultural empire, where beauty, technology, and global trade operate together on every row of land. If tulips demonstrate how the Netherlands transformed a flower into a global breeding and export industry, then tomatoes reveal an even bolder side of Dutch agriculture, turning everyday food into the product of precision farming. In many countries, achieving massive output requires fields stretching to the horizon. But in the Netherlands, just 14.5 hectares of greenhouse space can produce up to 100 million tomatoes each year. What is remarkable is not only the scale of production, but the way that production is achieved. Inside vast glass greenhouses, tomato plants no longer depend entirely on rain, sunlight, or natural soil conditions. Instead, they are grown in clean hydroponic systems where water, nutrients, lighting, and temperature are carefully controlled according to each stage of growth. As a result, these greenhouses use less water, significantly reduce energy consumption, and minimize waste throughout the production process. This is the defining difference of Dutch agriculture. Rather than forcing nature to work harder, they create an environment where crops can reach their full potential. And for that system to operate efficiently, everything must begin with something very small, yet incredibly important: the seed. But for every square meter to generate more value, the Netherlands did not begin with greenhouses or robots. They started with the smallest element in the field, the seed. For the Dutch, a seed is not simply planting material, but a biological blueprint that determines the entire future of a crop. How fast it will grow, how resistant it will be to disease, how much water it needs, and how it responds to light and nutrients. That is why the Netherlands has built an entire research ecosystem around the seed industry, where companies, universities, and laboratories work together to develop varieties of vegetables, flowers, and food crops designed specifically for precision agriculture. These seeds are created not to survive in unpredictable natural conditions, but to perform at their highest potential inside carefully controlled environments. Once placed in a greenhouse, they can respond extremely sensitively to even the smallest changes in water, temperature, or mineral levels. In other words, if the greenhouse is the body of Dutch agriculture, then the seed is the first brain that determines how efficiently that body can operate. But even the best seeds can only reach their full potential when placed in an environment that is clean enough, stable enough, and precise enough. That is why the Netherlands did not stop at developing high-yield crop varieties. They also transformed the very environment where roots grow. Instead of relying entirely on natural soil, where nutrients may be unevenly distributed, diseases can hide deep underground, and water can easily be wasted. Many Dutch greenhouses have shifted to hydroponic systems and artificial growing media, such as rock wool. From the outside, rock wool may look like simple phone blocks placed beneath the plants. But inside, it is an engineered environment designed to retain water, maintain airflow, and support roots in an extremely stable way. As a result, plants no longer need to search for nutrients in the soil. Instead, they receive precisely measured amounts of water, minerals, and pH levels directly at the roots. Excess water is not discarded, but collected, filtered, and circulated back into the system. This separation from natural soil has transformed the greenhouse into an almost closed-loop ecosystem, where growers are no longer at the mercy of soil quality or weather conditions. After the seed, this became the second step in the Dutch formula, creating a clean environment where every bit of a plant's genetic potential can be fully unlocked. But the Dutch philosophy of precision does not stop with tomato plants or growing substrates inside greenhouses. Once they became accustomed to measuring every drop of water, every nutrient level, and every small change in crop development, the Dutch extended that same mindset into a completely different field: dairy farming. Here, each cow is no longer managed solely through traditional observation and experience, but becomes an individual monitored through data. From feed intake, movement patterns, health conditions, and milk production to the smallest signs of abnormal behavior, everything can be recorded and analyzed before problems become serious. In modern farms, automated feeding robots move along the barns, mixing rations according to the herd's needs and ensuring feed is always within reach. In the milking area, cows can voluntarily enter the robotic milking system whenever they are ready, rather than being forced into a fixed schedule. The machines identify each cow individually, inspect the quality of the milk, and transfer approved milk into a closed cooling system. This demonstrates that Dutch agriculture is not only about controlling crops, but about redesigning livestock farming itself into an intelligent system. One where productivity, animal health, and labor efficiency are optimized at the same time. If the Netherlands represents agriculture built on precision in every square meter, then the United States represents agriculture on a massive scale. In America, the greatest advantage lies in its enormous farmlands stretching across states such as Iowa, Nebraska, Kansas, and California, where tractors, seeders, and harvesters can operate across thousands of hectares of land. This model relies on vast acreage, heavy mechanization, and highly developed supply chains to produce enormous quantities of corn, soybeans, wheat, beef, and dairy products. The Netherlands, however, has taken an almost opposite approach. Without endless stretches of farmland, the Dutch were forced to compress productivity into much smaller spaces. A greenhouse covering only a few dozen hectares must function like a precision machine where water, light, temperature, nutrients, and data are all tightly controlled. If American agriculture resembles a mechanized army moving across vast plains, then Dutch agriculture resembles a high-tech control room where every small detail is carefully calculated. Both systems generate extraordinary output, but through two very different philosophies. The United States expands power through scale, while the Netherlands expands productivity through control. Compared to the United States, Israel is actually closer to Netherlands in one important aspect. Both lack ideal natural conditions for traditional agriculture. Israel faces an arid climate, limited water resources, and large semi-desert regions, while the Netherlands deals with scarce land, high costs, and constant pressure from the sea. These very limitations have forced both countries to move away from conventional farming methods. Israel is well known for drip irrigation, water recycling, and solutions that allow crops to grow in water-scarce environments. In this system, every drop of water is delivered directly to the root zone to minimize waste as much as possible. The Netherlands follows a similar mindset, but in a different setting. Greenhouses, hydroponics, rock wool, and closed-loop water systems. If Israel has learned how to make deserts capable of supporting crops, then the Netherlands has learned how to turn limited space into a highly controlled production environment. What both countries share is the refusal to treat natural constraints as final barriers. Instead, they transform shortages of land, water, and climate pressure into reasons to invent technologies that many other countries would later adopt. What makes Dutch agriculture valuable is not only its output or exports, but the way it has created a reference model for the world at a time when land, fresh water, and labor are becoming increasingly expensive. Netherlands demonstrates that the future of agriculture does not necessarily depend on expanding land area, but can instead expand through knowledge, data, and control. Technologies such as high-yield crop breeding, clean growing substrates, water recycling systems, environmental sensors, and livestock automation are not only used by Dutch farmers, but are also studied and adopted by many countries to solve their own agricultural challenges. For water-scarce nations, closed-loop systems and precision irrigation offer critical solutions. For labor-limited countries, automation helps maintain stable production. For densely populated nations with limited arable land, greenhouses and soilless cultivation open up entirely new possibilities. In other words, the Netherlands does not only export vegetables, flowers, or dairy products. It exports a way of thinking about agriculture, producing higher value with fewer resources. However, the Dutch model is not a perfect formula that can be copied unchanged everywhere. Behind the bright greenhouses and data-driven farms lies a very high level of investment. A modern greenhouse system requires capital for reinforced glass, sensors, lighting systems, heating and cooling infrastructure, water recycling systems, control software, and a highly skilled technical workforce. This makes it difficult for many small farmers or developing countries to access without sufficient capital, infrastructure, and strong market networks. In addition, high-tech agriculture is not completely free from environmental pressures. Greenhouses may save water, but they still require energy to operate. Dairy farming can become more precise, but it still faces challenges related to waste management and animal welfare. Ultimately, it is the balance between technological ambition and real-world constraints that determines how far this model can truly go. From the vibrant tulip fields to tomato greenhouses operating like laboratories, Netherlands has shown that the future of agriculture does not belong only to the countries with the most land, but to those that use resources the most intelligently. When every drop of water, every seed, and every square meter is carefully calculated, even a small country can have a massive impact on the global food system. Today, even though polyester accounts for nearly 70% of global textile fiber production, thanks to its low cost and ability to be mass-produced from petroleum, cotton remains almost impossible to fully replace. Every year, the world consumes more than 25 million tons of cotton, and Xinjiang alone produces over 6 million tons annually, nearly equal to the combined output of the United States, Brazil, and Pakistan. But the paradox is this: to maintain the supply behind those enormous profits, humanity has increasingly pushed cotton cultivation into some of the driest and most extreme regions on Earth. But why? Stretching from Texas and Arizona to Xinjiang, Australia, and the Middle East, most of the world's largest cotton-producing superregions lie within semi-arid and desert belts. These regions span nearly 350,000 kilometers, equivalent to 1.7 times the size of California. In some places, summer temperatures exceed 50 degrees Celsius, the soil suffers from severe salinization, and groundwater has been heavily exploited for decades. Yet those harsh conditions also create an almost perfect blueprint for industrial cotton. Dry climates help suppress pests, reduce humidity that can rot fibers, and allow massive mechanized harvesting operations to run without interruption from rain. Even so, across the industry as a whole, cotton occupies only around 2.5% of global agricultural land, but consumes nearly 16% of the world's pesticides, making it one of the most chemically dependent crops on the planet. At the same time, humanity has also paid the price through one of the largest resource crises in modern agriculture: water. Cotton production alone contributed to the Aral Sea, once the world's fourth largest lake, losing more than 90% of its surface area in less than 60 years. As water increasingly becomes a strategic resource, the ambition to maintain massive cotton output without exhausting ecosystems remains a deeply controversial challenge for many nations. And to understand how this gigantic system operates, we must begin where every global cotton supply chain starts: harvest season. From around August to December each year, after cotton fields are chemically defoliated and reach the proper moisture level, gigantic harvesting machines begin operating almost non-stop across hundreds of thousands of square kilometers. Cotton strippers are commonly used in drier and windier regions such as Texas, where cotton plants are shorter and the fibers cling more tightly to the plant. Instead of individually picking the cotton, strippers use a system of metal combs and powerful pulling rollers to strip away almost the entire mix of cotton, dry leaves, and small branches from the plant in a single pass. This method is twice as fast and better suited for harsh climates, but it also generates far larger amounts of impurities that must be processed in later stages. That is why the cotton picker was developed and gradually became the dominant harvesting system across China, the United States, Australia, and many high-tech farming regions. The front of the machine is equipped with hundreds of high-speed rotating spindles that move between the cotton plants and continuously spin to pull the opened fibers out of the cotton bolls without destroying the entire plant. After being separated from the plant, powerful air pressure systems suck the cotton into onboard storage chambers, where the material is automatically compressed while the machine continues moving. Instead of collecting loose cotton and transporting it to a separate baling site, the machine directly compresses the cotton into massive cylindrical modules. Each module weighs around 2 to 2.3 tons, measures roughly 2.4 meters in diameter, and is wrapped in moisture-resistant plastic film on the outside. Once arriving at the factory, thousands of cotton bales are unloaded from trucks and stacked into long rows in outdoor staging areas. This is the first preparation step before the cotton officially enters the industrial fiber processing line. Next, specialized bale loader vehicles begin moving along the rows of cotton modules. Using hydraulic lifting systems mounted at the rear, the machines continuously pick up each cotton module and feed it onto integrated conveyor systems built into the vehicle. In a single cycle, the loaders can handle around 5 to 6 round cotton modules or even massive square bales, depending on the harvesting method used in the fields. At many modern facilities, once the cotton reaches the receiving area, the bales are further processed by specialized bale breaking machines, fully automated systems designed to open the compressed cotton modules. The machine operates by locking the bale in place, while an automated opening system removes the outer plastic wrapping, allowing the entire mass of cotton to fall onto conveyor belts leading into the feed hopper. From here, more than 15 tons of cotton per hour can be transferred directly into the factory's internal system without manual handling. After being tightly compressed throughout transportation and storage, the cotton modules must first pass through a hopper feeder system to loosen and separate the fiber layers. Inside the machine, high-speed rotating shafts combined with toothed bars continuously rake and pull the cotton apart from the compressed mass, while airflow and vibration systems simultaneously remove dirt, sand, dry leaves, and other large remaining impurities. This is a critical step that transforms multi-ton compressed cotton bales into a loose and uniform material flow before entering the fiber processing systems further down the line. Next comes the preliminary cleaning stage, where the cotton passes through industrial cleaning systems designed to remove remaining dirt, sand, dry leaves, seed husks, and fine dust left over from harvesting. Inside the machines, high-speed rotating drums combined with powerful airflow continuously loosen the cotton and separate impurities from the moving fiber stream. As a result, the remaining cotton becomes significantly cleaner and more uniform, ready to enter the most critical stage of the entire process, separating the fiber from the seed. This is the core of the entire cotton processing operation, where the fiber is fully separated from the cotton seed. Inside a modern cotton gin, hundreds of small high-speed rotating saw blades continuously pull the cotton fibers through extremely narrow metal slots, while the larger cotton seeds cannot pass through and are left behind. Even the separated seeds themselves go on to support a secondary industry worth tens of billions of dollars, ranging from cottonseed oil production to industrial livestock feed. However, cotton byproducts can also carry pesticide residues and agricultural chemicals accumulated throughout large-scale cultivation. After being separated from the seeds, the cotton fiber continues through the lint cleaner system, the final deep cleaning stage before baling. Inside the machine, multiple layers of high-speed rotating cylinders, combined with combing teeth and dust extraction systems, continuously remove remaining impurities, such as fine dust, broken seed fragments, and lower-quality short fibers. After being fully cleaned, the cotton fibers are compressed into large bales for storage and transportation. Inside the bale press system, powerful hydraulic pressure tightly compresses each mass of cotton into standardized metal molds before being secured with high-strength steel straps. Each finished cotton bale typically weighs around 220 kilograms and is labeled with barcodes, batch numbers, and complete technical data required for traceability and quality control. After passing inspection, the bales are transferred into specialized storage warehouses, equipped with strict temperature and humidity control systems to protect fiber quality during storage. Once orders arrive from spinning mills, the cotton is transported to textile manufacturing centers across the world, completing half of the journey that transforms raw cotton plants into fabric for the global fashion industry. The tightly compressed cotton bales are lined up in long rows before the automated bale opener system begins moving along each bale. Inside the machine, high-speed opening rollers continuously peel thin layers of cotton from the bale surface and feed them into the factory's internal air duct system. The cotton stream then moves through a preliminary loosening stage where rotating shafts and sweeping blades continuously break apart large fiber clumps into smaller clusters. At the same time, airflow systems and filtering screens remove remaining impurities such as dry leaves, seed husks, and dirt before the material advances to the next stage. All of the loosened fiber is then fed into the blending machine system, one of the most critical stages for ensuring the uniformity of the final cotton yarn. After the bale opening and blending processes are completed, the loosened cotton stream enters the carding system, the first major stage of industrial spinning. Inside the carding machine, multiple high-speed rotating cylinders covered with thousands of tiny metal teeth continuously disentangle, straighten, and reorganize the cotton fiber structure. As the material passes through this system, the originally chaotic fiber clusters are gradually transformed into a soft, uniform, and continuous strand called sliver, the standard fiber form used for the later spinning stages. The sliver strands are then fed into the drawing frame system, the stage responsible for stretching and aligning the fiber structure before spinning. Here, multiple sliver strands are combined together and continuously elongated through sets of rollers, rotating at progressively higher speeds, making the cotton fibers smoother, more uniform, and more parallel. In modern factories, the entire drawing frame system is typically operated automatically with electronic sensors monitoring sliver thickness in real time. As a result, this process precisely controls fiber density throughout each section of the strand, creating a stable foundation for the high-speed roving and spinning processes that follow. In the next stage, the cotton fiber stream continues through the roving frame system, where the fibers are further stretched and given a slight twist to stabilize the structure and reduce breakage during high-speed operation. All of this fiber is then transferred into the main spinning systems such as ring spinning or open-end spinning, where the material is drawn into extremely fine cotton yarn and continuously twisted at speeds that can exceed 20,000 revolutions per minute to create mechanical strength. Depending on the processing technology and intended application, the final yarn can be optimized for different characteristics such as softness, sheen, durability, or elasticity. Once the spinning process is complete, the finished yarn is continuously wound onto paper or plastic bobbins before passing through automated quality control systems. Here, high-speed sensors detect and remove defective, uneven, or contaminated yarn sections before the material moves on to the next stage of industrial textile production.